In this video, we're going to look at how we can take the reciprocal of a function. So we're going to consider the graph of y equals f of x. In this case, f of x is a quadratic, but it really could be any function. The principles that I'm about to tell you would apply to anything. And using that, we're going to sketch the graph of the reciprocal of this. So in other words, 1 over f of x on the same axes. So the thing to note about this transformation is that every point xy becomes the point x 1 over y. So the value of the function, in other words, the y value, is converted into the reciprocal for every value of y. What's going to happen very first off is because this now creates a rational function in this case, when f of x is polynomial, we still have the limitation that we would have for any rational function, which is that the denominator cannot be 0. But if I look at this function, there are a couple of spots where f of x does equal 0. Those are the x-intercepts. So right here at about 0.4-ish, and about there, say negative 4.4. I don't know exactly what those values are, but I know whatever they are, they've now created vertical asymptotes. So I have a vertical asymptote at x equals, like I said, about 0.4, and another one at x equals about negative 4.4. Doesn't matter what the value is. I can see on the graph that there is an x-intercept, so that becomes a vertical asymptote. Thinking through horizontal asymptotes, in other words, what value of y could I never get? When I have a constant numerator, which is the case here, I have a numerator of 1 divided by some number, whether that number is positive or negative doesn't really matter, is never, ever, ever going to equal 0. The only way to get a 0 from a division is if my numerator is 0. And since the numerator here is a constant, it can never be 0. So we are going to end up in each of these cases with a horizontal asymptote at y equals 0. In other words, no matter what the y value, 1 divided by that value is never going to equal 0. So now I'm going to look at some specific points, and I actually want to consider what are called invariant points. Invariant points are points that don't move. So points that are going to be the same on the original function as on the new function. So in other words, these are points. Now the x values are the same. So xy becomes x 1 over y. So x is the same. Where I'm looking for is where is y equal to 1 over y? Well, by solving this, I get y squared equals 1, which means y equals positive or negative 1. So that makes sense. 1 divided by 1 is still 1, and 1 divided by negative 1 is negative 1. So these are my invariant points. So on the graph of the original function, anywhere that y equals 1 or negative 1 is not going to move. So for example, we have points where y equals 1 at these 2 points, and y equals negative 1. These ones actually look like lattice points. So y equals negative 1 when x equals 0 and negative 4. But even if I can't tell the exact coordinates, I know that that's where those points have to be. I'm going to look at a couple more points, basically one more in each region. So this graph has, the asymptotes have divided my function into 6 regions. And the reciprocal function is going to exist in any region where the actual original function exists. So for example, in this upper left-hand region, the function exists, so the reciprocal of the function will exist. On the other hand, in this middle upper region, there are no values of the original function, and so the reciprocal function is also not going to be found in that area. So essentially we have 3 zones where the reciprocal function is going to exist. So I'm going to try and sketch a point or two, a couple of points in each of these zones so that I know what's happening. So for example, if I consider the points where y equals 5, there are 2 points where y equals 5. The transformed point is going to have to be y equals 1 over 5. So y equals 1 over 5. In fact, the higher the original y value goes, the smaller the new 1 over y is going to go. And the smaller the original y value, the bigger 1 over y is going to be. So this is going to look like what we've come to expect from rational functions. It's going to be a curve that goes through those points, specifically the invariant point. I have to be really careful about that, and approaches these 2 asymptotes. And the same is going to be true on the far left of the graph. I have a curve that comes down towards those asymptotes and gets quite close to them. In the central region, I know that I can't cross any of these asymptotes, so that already gives me some idea of the shape. But I'm going to look specifically at what happens to the vertex of the parabola. Because that is a critical point on my original function, I should probably figure out specifically where it goes in the new function. So the y value is -3, which means that the transformed y value would be -1/3, so roughly here. And because it was a minimum point on the original function, it's going to be a maximum point in this new transformed function. So I'm going to get a curve that kind of does this. It goes up towards that maximum, which is the transformed vertex, and then it approaches those asymptotes. Now, notice this is not the maximum of the function, because obviously there are y values in the positive on the far left and on the far right. But within this region, it is the maximum value of this function. It's easy to start to think of this as, oh, that's kind of like a parabola. It isn't a parabola. Parabola refers to a particular type of curvature, and parabolas definitely can't be bounded by asymptotes. But it is a curve that opens downwards, and so it has a maximum. So basically, any function that you have a graph of, you can graph the reciprocal. X-intercepts are going to become vertical asymptotes. The y-axis is going to be a horizontal asymptote. You're going to have invariant points where y equals positive or -1. And then you just sort of shape the graph based on where those asymptotes and invariant points are, but also look for specifically any key points.